Well, this week the topic is fiber, and I'm really pleased to have Benjamin Nemser with us from Namal Industries, Electronics. And in a lot of markets, fiber has not been all that important. In some, it's been very important, and in some, we're just about getting there. As I mentioned in the newsletter, try to get a copper phone line anymore. They've been ripping these things out left, right, and center, and that's not going to happen. But even in the broadcast studios and transmitter chain, uh, fiber optic is becoming more important. And so I think it's a good thing to learn about it. So let's turn our attention then to you, Benjamin. Tell us what we need to know, please.
Great. Well, first of all, Barry, thank you very much for inviting us to share this time with you and your group. I'm going to be giving a brief introduction to fiber optics as it applies to the broadcast world, whether audio, video, radio, television, and a few other related applications. And then after I speak for a few minutes, I'm going to ask our Director of Engineering, Danny Ritts, to give a hands-on demonstration, just for those of you who haven't had a chance to see what it actually looks like. Um, we're going to show you a fiber. We're going to show you some very simple cleaning that if you're going to work with fiber at all, you'd want to at least see what that involves. And then if you have any questions at all, please feel free to ask, and I'll do my best to answer. Probably if I can't, Danny probably can. Now, can I share the screen with my
Uh,
PowerPoint?
Absolutely.
Okay. So,
While you're setting that up, I'll ask the question. Do you want questions to come as they want, or do you want them to hold questions?
uh, well, they can raise their hands if they have a question, and I'm going to move through some of these things rather quickly. Um, this presentation has a few different elements, and we don't really have to get into the whole depth, but if anyone is interested in more detail of any of these subjects, please feel free to reach out to me after, and I'd be happy to, either direct you to some of our YouTube presentations or have a conversation over the phone. So
Excellent.
do you see the screen?
We do.
Great. Okay, wonderful. So we're going to talk about briefly evolution of broadcast. How did fiber get into our world? Because when I started 100 years ago, fiber basically did not exist. Um, some of the places we use it, some brief points about system design and installation, and trying to make all of this as practical and user friendly as possible. We're not looking to learn how to design systems. We're just looking if you need to have a conversation with someone in your team about a fiber system or possible future projects, at least a few questions you might want to ask. Some of the connectors and cables we use, and then of course Danny's cleaning. So I like to start the presentation with this picture. This was, I got invited by one of our customers, All Mobile Video. This is about 14 years ago, to film the second to the last launch of the space shuttle. And the interesting thing about this is that at that time, 3D was a very active and desired standard of transmission and data, video. So they filmed it in 3D. Now, 3D came and went just like many of the other standards that we have. And the point is that the standard we're using today is probably not going to be the standard of tomorrow. Again, starting with my history, and some of you look like you might be my generation, so you would understand. We started in the analog world. Now we're in the 12G and beyond, and there's an exponential change in performance and all of the other things involved in manufacturing, designing, maintaining these systems that we use in our world, audio, video, radio, television. To put a couple of numbers behind that, start with an analog data rate, 36 megabits per second. We're now up to the 12 gigabyte per second range. And a cable that used to handle, a typical RG59, better than 3,000 feet in the analog world isn't even usable in 12 gig. But if you were running a 6 gig signal, you might get a couple hundred feet out of it. So it really changes drastically the types of cables we need for our different signals. And all of you know the relationship between not only the bandwidth and the data rates, but also the return loss and the attenuation. This is our plant in Miami. I welcome any of you who ever get down here. It's kind of nice in the winter, not so much in the summer, to come and see us. So how this has impacted us and all of the other manufacturers in the industry is each time there's a change in standard and evolution to higher data rates, wider bandwidths, we need to change the materials we use. We need to improve the tolerances. The testing is all different. It's a whole range of things that we've had to do and continue to do each time these standards change, which they do regularly. This is one small step of the manufacturing process. It's braiding. All of you familiar with braids, but you may not realize that in a typical braid, like as this one, there's 24 of those bobbins, and each one of those bobbins has 11 strands of a 38 gauge wire. That's a pretty fine wire. So you've got hundreds of strands, they're crisscrossing, there's 12 going in one direction, 12 going in another, and we have to determine for each one of these cables whether we want to use the 11 strands of 38 or a 34 or a 36, whether different numbers of strands, different numbers of bobbins. Every factor that we change, even the angle of the braid, is going to impact the DC resistance, which is critical to us because a lot of times we're using braid for power return. It's going to affect the flexibility, the weight, the cost, and the diameter. So that's one small thing. Another thing that we have to juggle every day is which compound are we going to use? Now, all of us as engineers and people in this business know how to read a catalog, and you look for a spec and it says it's got a PVC jacket, it's got a polyethylene insulation. But what they don't often tell you is that each one of those things has a whole range of performance. You can get a PVC that's good for 105 degrees. Another one might be 60 degrees. Another one might be sunlight resistant, and so on and so forth. And each one of those things also has different cost, different flexibility, different size, and so forth. And those apply to both copper and fiber. So where are we using fiber today? Pretty much everywhere. The question would be, where aren't we using it? Now, this is a pretty cool picture that I took, getting intercepted by an F-16, but that was on purpose. These are the choices that we have today in our environment, in our industry. What cable are we going to use for high performance video or audio? You've got category cable, you've got coax, and you've got fiber. Let's look very briefly at those three options. For a copper cable, the category cables have drastically improved over the past few years. You can get a category 6A today that's going to give you great performance, but for short distances. You can also get the advantage of power over Ethernet, which is another plus that the copper cables offer that even the fibers don't. Within the category cables, you've got these different constructions. There's unshielded, there's individually shielded, there's overall shielded, there's solid, there's stranded. So when you're buying a category cable, you need to know which one of those things do you need, because they make a drastic difference again, cost, size, weight, flexibility, and so forth. Let's put some numbers behind the category cables. Take a Cat 5e, which for many, many years was a very common bread and butter cable. Maximum frequency 100 megahertz. You go up to a Cat 6a, it's 5 times that much. It's 500. The same general improvements with other specifications as well. The category 7s are getting even higher, but now you're talking about a much larger, much more expensive cable, but you're going to get some more distance. And then the Cat 8, which I have seen only a piece of, we've never actually sold it. It's got some drastic improvements in performance, but only over limited ranges, not everywhere. Some of the other standards, you got the HD base T. It's a very common standard for ultra high definition video. great to use with Cat 6a, and it'll give you 4K uncompressed video. Here's your Cat 6s, and in the family of Cat 6s, as I said, you have a lot of options, and one of the things that's really made it a lot more friendly for use in the field is these really cool Ethercon shells that go right over your RJ45s and protect it. Another standard, we've got IP, AV over IP with Dante, which a lot of you have probably used. So now let's look at some of the coaxes. What's happened to the performance of coax as we've gone through this evolution of standards? Well, I like to use an example of an RG6. Those of you who know Belden, it would be a 1694A. So in the old days, the NTSC, never twice same color, 143 megabit per second, average data rate. You could get 544 meters, figure, close, just under 2,000 feet of distance with a usable signal. By the time we get to 3 gig, we've lost 85% of our distance capability. Even with the larger cables, the relationships are pretty much the same. You can see that all of the standard cables don't even have an entry at the 12 gigabit range because they're just not made or tested for it. So we have some specialty cables that we make and others make for 12G, optimized for 12G. And you can see the last 3 entries on the chart. So in the larger RG6 version, you might get 89 meters. Now, when I say might get, what I mean is we read these charts, we make our plans, we do our designs. This is rated to this. That rating is on a perfect day when the sun is shining, when you've got a perfectly terminated connector, it's got no bends, and everything is beautiful. Any one of those things that's not in place is going to reduce that distance. The other thing about the distance that I really like to point out, and I've got a slide for it, is that that distance is based upon one connection point. As soon as you start adding more points, those numbers are going to go way down. And the more points you add, the lower they're going to go. We've had a number of systems integrators that we've worked with that have had some pretty serious issues with not accounting for those multiple interconnect points. The other thing is you'll note that there's a general standard for 12G, but everybody seems to kind of come up with their own standard. So one person's 12G is not really the same as somebody else's 12G. So you need to read the specs and see what it is they're calling 12G. Whether it's a Belden, whether it's us, whether it's someone else, and the same thing with connectors. And the final note is the BER, the bit error rate, can vary dramatically as you approach these calculated limits. Same issues as cable apply to connectors. The point I like to make here, to try to at least, if I can save one person a headache, it'll be worth everything. BNCs, when I started in this business, were plain simple. Everything was 50 ohms. You didn't even ask the impedance. That's what it was. That's what everybody used. We got into video, analog video, you could use a 50 ohm VNC. You could use a coat hanger. It would work. When we made the first transition to digital, connector people, and we manufacture connectors as well, decided, well, we need to really use 75 ohm BNCs. So we started making them, but they were nominal 75 ohm, plus or minus 10%. Then we get into higher data rates. Well, we need to really bring that tolerance in a little bit. So we tightened the tolerance to plus or minus a couple of ohms. Precision BNCs. Now we're in 12G, where we have special BNCs made for 12G. Now, all of those BNCs will intermate with one another. The 50 ohms, not with the 75s, obviously, but the other ones will, but the performance is going to be different. There's a whole other family called an HD BNC, and that really doesn't mean high definition. It really means high density. But some people call it a micro BNC. Some people call it a mini BNC. The bottom line is, if somebody says, I want one of those 12G BNCs, please figure out which one of these they want, because it could be either one, and those do not intermate. And there's a big difference in price. And if you're on a deadline to get something built or a studio working and you get the wrong ones on a weekend, which is what happens, you might not be too happy. Um, you can see the pretty big difference in the return loss of these things. In one case, a 12G is rated at 15 dB return loss. In another, it's the other version at 30. Now, just to give you a point of comparison, we get into fiber. The minimum return loss for the SMPTE fiber standard is 45 dB. So starting to look at some fiber. Um, Typical snake, audio snake cable you can see there, and you can see that little yellow line of fiber, which is going to do much more data for much greater distance at a much higher bandwidth than that cable and cost a lot less. And that's just one of the reasons that we go to fiber. The fiber cable today is much, much cheaper. The distances are really hard to fathom. So some of the considerations we're going to use with fiber. Here's my example of multiple interconnect points and why it's so important to control the number of points, because each one of those points is a possible point of failure. One bad connection in a line is going to probably mess up the entire signal path. So when you plan these things, or if you're redoing something, a couple of key points, whether it's fiber or copper. Be really precise on your terminations, minimize the connection points, use enough cable to do the job, but not excessive cable, and don't compress the cable. I've seen beautiful racks, and the work is absolutely impeccable. And you can see the cables in all the colors, and they're lined and they're going down, and there's hundreds and hundreds of cables, and they got tie wraps every 6 inches exactly. Well, guess what? They were a little bit too tight, and you just made a filter for whatever that frequency is for that distance interval, and something's not going to work properly. Some other considerations for cable, and again, this applies whether it's fiber or copper. UL. UL is something, as a cable manufacturer, very near and dear to our heart. UL used to be a nonprofit organization. Now it's a very high profit organization. But basically, their job is to certify that the cables that we make or any other manufacturer make meet the National Electric Code. Typically, the National Electric Code is the code in force in most cities and states in the United States. There are exceptions and there are things in addition to that. But as a general rule, a city says our electrical code is the National Electric Code, but they have no way to verify that a cable that you're installing in your building meets the code. So that's why we use these independent labs. And it could be UL, it could be ETL, it could be, Intertech. There's several other ones that do that. And it is very important to us working in any kind of facilities, broadcast or event venues or otherwise, to know what are the requirements for cable that I'm installing. Am I installing something that's outside, never going to go in? Is it something that's going to be within a room? Is it going to go between floors, or is it going to go in a return air plenum? Each one of those categories has a different rating and a different standard and different testing. And I have seen people very, very upset after they've done major wiring in a building and an inspector's come in and said, you really needed plenum here and you didn't put in plenum, so it's all going to come out. And they will do that. And plenum, for those of you who may remember, many years ago, there was a fire at the MGM Grand Hotel in Las Vegas, and a lot of people died. And they died not from the flames, but they died from the smoke. The smoke went through the whole building very, very quickly through the return air plenum, which is the moving air coming back from the HVAC systems. And that's, as a result of that, the National Electric Code changed, and it required these more stringent testing. And in fact, the smoke testing is the strictest testing of all of it. Another consideration with fiber is cleanliness. That took a long time to pose him, but you have to, if you work with fiber, make sure that you clean every single time you connect or disconnect a connector. And Danny will show you a little bit more about that. We've got all types of cleaning things. There are all types of things that can go wrong with fiber. I'm not going to bore you with those at this point, but I would like to show you this cool picture of the way we test are SMPTE cables, and it's with a device called an interferometer. It costs about as much as a normal car today, but it measures the geometry, not just the attenuation, but the geometry of the fiber polishing to make sure that everything meets all the standards. And you're talking about measurements in the millionths of a meter. It's really cool. So very briefly, someone asks you to get fiber. What are the basic questions you need to know? First of all, is it single mode or multi-mode? Is it breakout or distribution? And is it any special particular variation of those? So the two basic constructions of the actual glass fiber, single mode and multi-mode. Multi-mode was the first, and it was between 50 and 62 and a half microns in diameter, typical. Multi-mode worked okay, but single mode is much, much better in performance, and single mode is now much less expensive. Single mode, instead of 50 or 60 microns, is 9 microns. It's narrow enough so that instead of the light bouncing, as you can see with those arrows, it's one single path. And around that 9 micron is a cladding. It's a opaque material to hold in the light, and that's 125 microns. And that's the smallest thing that you can really see. You'll see that in a slide in a minute. And then over that are additional coatings. So what you're looking at here is the little piece of glass that you can see going into the contact is the 125 micron. Inside of that is the 9 micron core. And then the blue coating is a 900 micron coating over the cladding of the fiber. And that's a F2 contact for fiber. So the different types of fiber. Single mode, as I mentioned, I told you that it was a lot higher performance, but again, putting some numbers to it. 80 kilometers of distance as a general number at 10 gigabits per second compared to a multi-mode fiber of 300 to 500 meters. So you're talking about hundreds of times longer distance. And the bandwidth is pretty much unlimited, 100 terahertz, if you can imagine, at the typical wavelengths. And for those of you who like RF, you're talking about wavelengths that are a micron, 10 to the minus 4 meters. They're pretty high up there. So now we know whether we want single mode or multi-mode. The next question would be, do we want distribution fiber or breakout fiber? What you're looking at now is a distribution fiber. It's got multiple fibers, and it could be any number, individual, typically colored coatings, and that's just like the slide we saw previously. And those are all in one jacket. And those cables are usually pretty flexible, depending on the number of fibers, but they're low cost, they're lightweight, and they're good for going long distances where either you have protected termination areas and not a lot of termination areas. So this you would find in tactical fiber and long distance telecommunication fiber. The other type of construction, which is breakout fiber, gives you a jacket around each one of those fibers. And that makes it really easy to terminate. But it also makes the cable a lot bigger, a lot more expensive, a lot less flexible, but easier to terminate. One of the most common things that we buy in fiber today are patch cords. There are thousands and thousands of varieties of patch cords. And if you're going to buy some fiber, that's probably one of the things you're going to buy. So if you want to buy a patch cord, some basic questions. Same original question, is it single mode or is it multi-mode? Do you want a patch cord that's never going to move, that's going to be in a facility like an IT rack where it can be a small, lightweight cord like a 1.6 millimeter, which is fragile but small and flexible? Or do you want something that's going to go out in the field, that's going to move around a lot, where you really want to pay a little bit more for something that's going to hold up, and you want typically a 3 millimeter. A lot of times they don't tell you that when you go to buy these things. So that's one question. Then, of course, it can be a single fiber, simplex, or it can be two stuck together, a duplex. It can have any types of connectors on either the same on each end or different ones on different ends. And the polish, and in this case, the green indicates a special polish called an angle polish that's available in some connectors. So those are some of the questions you'd want to know. Those are your individual fiber connectors. Now we get into the specialized broadcast connectors, and you're looking at a broadcast camera. If any of you have seen these, you certainly see them at all the shows. But this connector is called a hybrid because it's got fiber plus copper for camera power. And there's 4 conductors, a copper and 2 fiber contacts. They're single mode, and these are pretty standard. They're not the only ones available, but they're the most common ones, the Limos and the Canaris. There's also, we'll see the optical cons in a minute. And these are your individual connectors that could be on any type of equipment, whether it's a Blackmagic or any type of a prosumer unit. You've got 2 that are plastic, the SC and the LC, 2 that are metal, which are a lot more robust, the STs and the FCs. And then you can see the ferrule, it's 2.5 millimeters on the 3 of them to the left, but the one on the right, the LC, which is really small, is half the size. It's a 1.25 millimeter ferrule. Why do I say that? Because whenever you buy cleaning supplies, testing equipment, or so forth, you need to get the appropriate supplies for the size of the ferrule you have. So an LC ferrule is not the same as the other ones. You typically have to buy 2. There's a lot of multi-fiber connectors on the market. MTP is something that's becoming much more popular today. We just did a major broadcast facility. It had hundreds of these. These are either 12 or 24 fiber, single mode or multi-mode, and polishes are available standard or APC. Close-up view of the Limo, you can see the 2 ferrules. Those are 2 millimeter ferrules. They're not the same as any of the standard fiber connectors, so that's why they need separate testing equipment, separate cleaning equipment, and so forth, but they're pretty cool. But if you have one of those and you need to adapt it to something, we make all types of adapters that'll allow you to convert the Limo fiber to a normal fiber that is user-friendly. The same thing with hybrids. We have all different types of cables made to individual customer requirements. If you're in a radio station and you want a cable that's got a Cat6 or a couple of Cat6s, plus a power, plus a video, plus a fiber, you can have it all in one jacket, terminated any way you want. Another variation of hybrid cables is the multi-channel SEPTI cables. And they come in 3 or 4 channels for cameras. The same thing applies to panels. You find panels today in any broadcast facility. 99% of the time, they're going to include not just one type of fiber, but multiple types of fiber. Here you see MTPs on the upper right, 12 channels. And on the left side, you see optical cons, which are 2-channel fiber. And in many cases, you're going to see STs and other connectors in there also. Another type of construction of fiber that is in the broadcast world that you may see is called expanded beam. And without getting into a great deal of detail, you can see the top part of the slide. All of your typical fiber connectors are direct physical contact. It means the ferrule of one touches the ferrule of another. They have to line up perfectly because there's only a 9 or a 50 micron space there to line up. And it's very efficient and very low loss. However, it's also efficient for transmission of dirt, and it's also much more susceptible to damage if you don't make them properly, if they're not built properly, and so forth. So some really smart engineers came up with this idea. Let's protect the ends of the ferrules, and let's put lenses and mirrors there, and let's just make that 9 microns really big so that there's lots of room for light transmission, and that works for many applications. However, you do pay a price in size, cost, weight, and so forth. And this is just one variation. But to illustrate what that concept does is, see on the left, you've got your normal direct physical contact. On the right, you've got an expanded beam. And let's just say that you had one tiny speck of dust. If the tiny speck of dust went right over the center of a normal connector, there goes your light transmission. But if it goes anywhere in the surface of the expanded beam, you've only lost a small fraction of your light. But you do pay a big price in attenuation. I'm not going to go into those specs, but for many applications, you've got the attenuation budget, you can live with it, and it's a really robust and very user-friendly solution, very easy to clean and maintain. Optical con's a whole family of fiber connectors. I'm not going to go into lots of detail now, but just so you know, if someone says optical con, I'd like to point out one key thing. There's optical con that is fiber only. They come in multi-mode or single mode. And if you see this connector, it's called a duo, and there's two fiber contacts in the middle in the rectangular area, which are standard LC contacts, which are really easy to use. And there's 4 little holes on the bottom. Well, those 4 little holes can have contacts in them or may not have contacts in them. If you're powering a camera, you need to have contacts in there and have copper. If you're not powering a camera, you don't need them. So you wouldn't believe that people who did have cameras ordered optical cons and didn't really say what they needed and got the ones without the power, and their cameras didn't work. Surprise. So just so you know, but if you do have optical cons, you can buy the receptacles, you can put them in any standard mounts, and you can put your own LC connectors in the back and move them around. And if you need adapters, we have all these adapters that'll allow you to convert them. Media converters are another big thing. They are available for pretty much any kind of standard data transmission you have. If you've got an HDMI, if you've got, you want to extend category 5 or 6 cables, if you want to extend, normal 3Gs, 12Gs, you buy these media converters, they convert it to fiber, you go for miles, and at the other end, another one converts it back to whether your audio, standard audio or video or HDMI or whatever connector. So the overall theme again is that every time the data rate increases, the distance that copper will work becomes less, fiber becomes more important, and it's something that we're probably going to see more of in the future. The data rates that started out at way under a gig, that are common at 12, pretty common, very common at 6, are now looking at, for the 8K, 24 gigabits. So fiber's definitely there. If anyone has any questions now, please go ahead. Otherwise, I will ask Danny to take over. And Danny should be here somewhere.
I'm here. Can you hear me?
Danny's-
How is my audio?
Oh, there's Danny. Okay, cool.
How's my audio?
I hear you fine.
Okay. I have 3 cameras plugged into a laptop, so bear with me for a moment. Oh, lovely. I'm trying to figure out how to switch between them. I couldn't do it before. There we are. Howdy, everybody. I'm going to demonstrate different cleaning techniques and show you the surface area of some contacts. I'm also going to show you magnification of those contacts so that you have some idea of whether or not you're actually achieving any cleaning or actually making it worse. And in most cases, people don't have best practices. In other words, a technique that actually works, and it's very connector specific. I'm not really sure that you guys are into, because Ben tells me this is more of an RF radio people, but I do know that you are going to run into individual connectors, STs and Frank Charlie's, Sam Tom, I say everything phonetically, and Sam Charlie's, and Lima Charlie's, the little ones. But the hybrid connectors you may not run into, but they all require special tooling to be able to access their contacts. And I'm going to quickly demonstrate that as well. And most importantly, is I'm going to show you a tool that basically everybody has to have, because if you cannot visually see the face of the contact, then how do you know that you've actually achieved anything? So I'm going to switch camera positions, and I'm going to show my hands and show you what tools I'm referring to. Let me, bear with me. Okay. As Ben was discussing, we have different types of contacts in different sizes. LCs being the 1.25 millimeter, you'll notice it's half, and this being 2.5. So it's literally just half the surface area of the contact on these. So you've got this being a 2.5 millimeter ferrule and that being a 1.25 millimeter ferrule. And being able to inspect them is probably the most important part. And that's why a video scope is pretty much a necessity these days. Being able to visually see the surface of a contact. They do have handheld scopes. They max out around 400 power, if they're really that. The detail is very poor and it's very cumbersome. And it's almost impossible to use a handheld manual video scope when you're trying to inspect chassis mount receptacles. Video scopes give you the ability to actually, with different tips, be able to look at chassis receptacles, be able to reach inside different receptacles, and actually look at a recessed contact inside of a connector. So what I'd like to do is I'd like to show you the surface of a contact by, again, switching camera angles. Okay. You see in the center there, that is the core of the contact. The rest of that is the cladding material and epoxy that suspends it in there. But that tiny little speck of light is all that's relevant to us for passing light. However, all of that other debris you see on the contact, and this is a fairly new contact, off-the-shelf jumper cable. I may have actually left the contact's dust cover off of it for a couple of minutes, and it collected dust. And it is one of the things that is imperative that I discuss with best practices is being diligent about cleaning something every time you made it. If you unmade it, wipe it down before you remade it. And if you have the ability to visually inspect it, so that you know that it's clean before you made it because of transference. If I were to accidentally touch the surface of the contact like I just did now, that is what my finger just did. A momentary touch of what I thought was a clean hand, I accidentally touched the surface of the contact. And that's what it looks like now. And if I just go ahead and mate it to its corresponding receptacle, I will transfer about 50% of that junk to the other contact. And I will leave it that way, and they will cook and bake together until they're almost impossible to remove. So it is really optimal to have a best practice, and that is if you unplug it, clean it before you plug it back in. I'm going to revert back to my hands here, switching camera angles. There are several different ways that you can clean the surface of a contact. There are basic wipes. This is nothing more than a non-woven fabric that's used to wipe down the surface of something. Some of you may be familiar with chem wipes, which are very popular for lens cleaning, so it's non-woven fabric. You can also buy it in a box form that gives you the ability to simply wipe the surface of the contact down. This is the contact that I touched the surface of. And I'm going to give you an idea of what that little wiping did. Hopefully it doesn't embarrass me. Okay. Unfortunately, that is lint, even though this is supposed to be a no lint product. But do you see how much I removed? I will do it again. I'm going to touch the surface of that contact again and show you what I did. All of that's the crap that just came off my hand. So again, going back to cleaning it. This is an unwoven fabric in a box. We sell these. Companies called Stickler. They sell a number of different things. They also sell a stick. The stick has a fibrous material inside of it that gives you the ability to scrub the surface of a contact. If you work in the field and you're using these things as patch cords and you're mating and unmating, you're going to have to learn to scrub. And it is apply the stickler and rotate one direction to basically bring the dirt from the inner core to the outer core. Predominantly, we use alcohol in almost everything. I buy big containers, denatured alcohol or 99% isopropyl alcohol. You can also buy dispensers. This is it is alcohol, but it is a very fast drying. If you've ever used like carb cleaner or something, this evaporates and is pretty much bubble free. Now, 1.25 millimeter is an unforgiving contact. And yes, you can buy for any type of video scope tips for pretty much every connector you could possibly imagine. And you simply swap them out. I'm not a big fan of LC connectors. Unfortunately, they belong on a lot of SFPs, but since we do a lot of remote broadcasting, people tend to use them like they're field connectors, and they are not. They're made of plastic. They're easy to break. I'm a big fan of ST. If I could show you behind me, I probably have 20 reelers to repair of broken LC connectors that somebody's trying to use for remote broadcasting, and they don't hold up. In most cases, I try to convince the customers to let me take and design them a patch system that converts the LC interface to the BNC, or excuse me, the ST interface, which is like a BNC, so that we can convert everything over to a standard ST, which is a much hardier connector. But like the ST, you can get a tip for pretty much any visual inspection. I'm going back to the camera here. Okay. Now, you can see surface area on that. These are my props, so they will be a little dirty, but I'm going to touch this puppy too and visually inspect it again. Okay. They get wiped out really fast. Okay. And unfortunately, these connectors are usually device to device. An LC connector often is mated to an SFP. SFPs are very hard. That's part of the transceiver gear. That's your optical output input. That is part of the gear that is very hard to clean. And so is this connector. My favorite for cleaning these connectors are string cleaners. String cleaners are literally basically the design like dental floss. Inside of this is a small spool of string, and it is aligned to the surface of the contact and drags it across it, literally centering the floss directly over the surface of the contact. And we call them one click. It's a trade name, because it goes snap, snap. Snap. This one. Okay. We're going to go back to this. That's probably the simplest cleaning technique that you can have. And there we go. For the surface area of the contact. So I'm a big fan of the string cleaner. And again, you can buy these for everything. In other words, for the 2.5 millimeter, the ST, for the F2, which is inside of the hybrid broadcast connector, for SEMTI, and they also work inside of, I'm going to pull out a hybrid connector, the one we were discussing. I'm going to show you that how you get access to it, and it requires, again, some type of specialty tooling to expose the contact. but that basically retracts an internal sleeve that gives you visual inspection of the contacts. I'm going to manually do it, but down inside there are two LC contacts. And in order to properly clean them, you have to retract them. There are several different ways to do that. That being the easiest one, shows you two LC contacts, and then the same thing. You reach inside, click, click. You can wipe things down, but more often than not, the process, especially chem wipes, are infamous for it. These draw moisture out of your hands so quickly and the oils out of your hands that by the time you're actually touching the surface of the contact, you're actually transferring the oil you just put on here. So you will go through cases of these. Whereas something like this, a tearaway of non-woven fabric to wipe it down, or a string cleaner, you basically don't interact with the surface area of the contact. So now, if you develop a situation of best practices where you're cleaning a connector before you made it, if you unmade it, you clean it again before you remade it, you won't run into issues like we often do, where we're trying to clean something that is actually like calcified. The material that was transferred to the surface of the contact has sat on it so long and under pressure that it has bonded, I'm transferring lenses here, to the surface area of the connector. And unfortunately, it is going to require a lot more scrubbing to get off. And in some cases, a little bit more termination. Thought I had an ugly one here. There we go. Of the connector. So I'm going to give this one a quick wipe down. And I don't know why I did that. I don't know why my video dropped. Okay. No, this one's not calcified. I wish I had a better example in front of me, but I don't. But my point being predominantly is that once you've contaminated the surface of the contact and then you've mated it and it stays mated for an extended period of time, I have no idea why it's doing that. And it stays mated for an extended period of time, it will actually bake on. It will be horrifying to actually clean. You will have to spend 10, 15 minutes per contact to clean them, which is excessive. And they'll still not be 100% in either case. So I wanted to also show you, because he touched upon it, expanded beam interface, because it's a completely different technique. I have one here. Expanded beam is literally the contact lens. There are two balls there, and behind them are the glass, or the fiber contacts themselves. They can be 2.5 millimeter, they can be 1.25. That's not really relevant. But the benefit is that these contacts, the surface area of it, can be cleaned simply by spraying it down. Unfortunately, this is two focus lenses facing one another, so it's a high attenuation connector, but for field use and for ease of cleaning, this is probably the preferred way to go. However, it does come with a large startup cost, and it can be tricky to put it back together again. So I can't actually think of anything else off the top of my head. So I'd like to take any questions if anybody has any at this time.
If you have a question, you can raise your hand, or you can press your space bar, alternate A, will open your microphone. We have a comment over here in the chat about I was always fighting against our live van operators, dragging those MX connector ends through the dirt and mud puddles.
Yes, unfortunately, there's not a lot you can do about that. So that's a side effect, but it should be very hardy, the MX connectors, and tolerant of that. If you keep employing, them people and those cables, I would suggest you buy them with drag boots. Drag boot is like a Mueller large rubber boot, that actually will go on before the connector is installed, that basically shields it against, the asphalt or the concrete drag. So, and you can buy a Mueller boot, what I call a drag boot, in almost every size.
Okay. Harold, you've got your hand up here.
Yeah, the expanded beam thing is interesting. Do they have a problem with reflection and return loss and so on, or is the return loss still okay?
No, it's awful. The insertion loss and return is awful. However, is an acceptable level and it stays moderately fixed. In other words, it is inherently poor as a connector. I mean, by standards of all the other connectors, with 45 to 65 dB back reflection and losses in the hundreds of a dB. They unfortunately can, right off the bat, you're going to have a dB. Every mate, it's going to cost you a dB. And if you switch between brands, in all honesty, you're going to notice that one brand doesn't mate and seat as well with the other brand, even though they're supposed to be industry standards. And they could be as much as 2 dB. So you're just going to have to budget for it. But once you budget for it, it's consistent. Whereas if you keep using and reusing cables that are positive engagement, positive contact, a lot of people are not even aware of the fact that fiber contacts actually are hard compressed to one another. I've talked to people in the field that had no idea that the two contacts are pressed against one another in the conventional world. Whereas expanded beam is two lenses looking at one another, and you can wipe it off and spray it out like with air and a little bit of alcohol. So it is consistent if you budget for the loss, but it is not the performance. No. Does that answer your question?
Yes, it did. And these are generally being used single wavelength, or is there wavelength multiplexing going on?
All of the above. I've done kits where they, did, course division multiplexing and stacked. They had, 16 different devices coming back over 2 fiber. That's all on the electrical end. The glass doesn't care how many times you stack it, as many frequencies as you want.
We have a question here from Dustin. He wants to know if you can recommend a basic troubleshooting toolkit for doing maintenance when you have a lot of fiber in your network. He said, we're owned by an ISP, but it's helpful to be able to do some basic troubleshooting.
Well, a kit. No, meaning I can't say everything we do is custom per the application or the user's need. In his case, if it's infrastructure, he's probably more leaning towards multi-mode or device to device versus a telecom long haul that would be single mode. But the video scope is an absolute imperative. String cleaners are an absolute imperative. Then you've got insertion loss gear. In other words, you want a meter and a light source. That is the same as multi-mode or single mode, what you're using in-house. So, but you can cobble it together, or you can give me a call and I can discuss specifics. I can't say that off the shelf I've ever seen a kit that I was pleased with. No, I've always put them together.
That makes a lot of sense. When you start a new facility, let's say we're rebuilding a radio studio.
Yep.
Basic. What would you recommend? Where would you start? Would you say that we have to have a certain, you say you don't like those LCs.
No, I don't like the LCs for the field application. I've got them on reelers behind me, and they're trying to use them for remote broadcast. and you step on them and they just get crushed. They're like an RJ45. They require a snap latch that's made out of plastic. So for high density infrastructure inside of a facility, they're fine. Plugged in, left alone, they're perfect. They don't belong in the field. They don't belong in the sun. They don't belong in the rain.
Something more robust for that kind of an application.
The ST is fine. It's a copy of your basic BNC connector. It's a bayonet lock. There are the connectors that have better performance, however, they are more difficult to seat or they're made of plastic. And in both cases, they don't belong in the field. Design around STs because you can go to any rental house and rent a couple of 1,000 feet of TAC 12, TAC 24, whatever. And I can teach anybody to field terminate an ST easily. But yes, if you're going to build or start a plan for building an infrastructure, I would design around LC if I had high density or Sam Charlie. I'm a big fan of Sam Charlie because of bend tolerance. When you mate an LC, Lima Charlie, and bend it right or left, you will get weird attenuation issues. The Sam Charlie, which is its big brother, is another plastic connector twice the size, but when you engage it and you bend it or dress it, it will not attenuate. But it's made of plastic and doesn't belong in the field either.
Okay.
The question, as long as you mentioned terminations, when I initially got involved with the fibers back in the early 2000s, and terminating a piece of fiber was a bit of an art, actually. And I'm wondering if here we are in 20 us to properly terminate a piece of fiber into a connector, or if that's still somewhat of an art to make a good connection termination.
I would say that we've advanced tenfold in machinery to support good termination. If you want to invest money up front, you can fusion splice all your contacts. You can put pigtails on. You know, you drop 7 to 10 grand, you get a fusion splicer and you buy tails and you can put on 24 ends and all your ends are going to be perfect. Why? Because, you know, they're already pre-done by a factory and you fusion spliced them on, which is a great option. But if you need something that's hardy, field deployable, you know, not plug and leave alone, then you want to do epoxy polish. And you can get into the epoxy polish game for a couple of grand. And the machinery does it. You just follow basic steps. And really, the advent of video inspection has really been the groundbreak on that. And the test gear has gotten dirt cheap. Meters are peanuts. Light sources are a little more money for a good calibrated light source, but it is all very inexpensive. So no, I would say that I can field terminate with hand polishing, a couple of pucks. I can do it for a couple $100 and be competitive, especially with a machine, especially if it's for field application. In other words, I'm going device to device. I'm plugging from my truck to my remote box. Okay, I don't need better than 25 dB back reflection. So I'm gonna whip them out hand polished. So I can do it, and in relative ease, I can put them on as easily as I can put on a BNC. I've been doing it a long time, but it is not challenging like it was before. So the films have improved, the rubber pads have improved, the polishing pucks have improved. But if you want to get into terminating an entire building, an entire fiber house, put on a few thousand, so you want to invest in a bench mount polishing of gear and stuff like that. I tend to tell people, if you want production and it's your house, go with fusion splicing. We do epoxy polish because it's a necessity of the type of connectors we do and the fact that we're field deploying these connectors, so they have to be hardy. But if you've got racks to dress in, I like fusion splicing because you can buy 65 dB back reflection angle polish connectors that have 0 loss, fusion splice them on, and I can show you, through 5 patch bays, device to device, that I lost 2% of my signal. Nothing.
I notice when you bring in a new circuit from a telecom or something like that, they'll always come in with a pigtail and a fusion splicer to do it because it also gets them in and out of the facility in a relatively short period of time.
Yes, it is time saving, very consistent. Now, I mean, we also have Unicam or a Unicam design where the connector in and of itself is the fusion splice. There isn't even a tail. I like tails because I have to fix things all the time, so I can reuse a tail. A $20 fusion splice connector only gets to use once.
Thank you.
That only makes sense to have the right tool, and cheaping out on the cheapest tool is not going to do you good in the long run.
No.
Very good. Any other questions from the floor? We have a chat recommendations for a direct burial fiber at an AM site, assuming 110 meters, 360 feet, and then crossing the base insulator 40 feet from one end.
Okay, well, burial can come in many different styles. So there is gel filled, loose tube, tight buffered. I mean, depends upon how it's going to be broken out at the end. So there's no end to it. Armored, non-armored. If it's in conduit, is it direct fill? Is it sand fill? It's hard to say. It depends upon the exact situation. Are you intending to terminate it on site, or do you want to pull something that is pre-terminated?
John, can you answer that?
All right, yeah, I'm getting on the microphone now. I would actually be open to having something that's pre-made to that length, so I didn't have to terminate it in the field. Yeah, it's just a plan to be able to put a WISP type of 5 gig dish up on the tower and to be able to convey that data into the transmitter building. And I thought, well, maybe instead of doing a second hop to the transmitter building, why not just go with fiber and just, yeah, as for the burial, it would be backfilled with dirt, and unless it is imperative that you put it in conduit.
No, it's not. You can get direct burial, and you can get it armored and non-armored. Armoring, I suggest if you're going in with rock. And it's going to get paved and driven on regularly, and you're not going to get more than 13 inches below the surface. So, and I don't know if you can see that's piece of 7/8, and I replaced it with one piece of glass. This had 10 dB of attenuation. This had 1/10 of a dB of attenuation. One fiber. Incredible trade-off.
Yes, indeed. And in our
back-
case, this would be in a pasture that gets occasional sporadic traffic from lawnmower, tractors, or whatnot, but not generally traffic.
The fact that you need to get across the base insulator sounds like you can't do at least metal armor. I don't know if
Yep.
there's anything else. And then also, is stuff that's designed for direct burial, how does it do when it's not buried under ultraviolet light of the sun by these?
The jacket
compatible?
compounds are usually polyethylene. It's the same thing everything that's up on the telephone poles. It's living there forever. So it's also a polyethylene jacket material most of the time. It'll outlive us all.
Okay. Ben, do you have some contact information you'd like to put up on the screen here? And
Nothing to put up on the screen, but our website is nemal.com, and we're very easy to find.
nemal.com.
.com. Yep, you can find us there. You can find all of our contact information. We'd love to hear from any of you, or again, if anyone gets down here, we'd love to see you. And otherwise, we go to a lot of the trade shows. We'll be at the NAB in Las Vegas, the NAB in New York, the Infocom show coming up in Vegas, and a lot of the regional shows as well.
Well, I sure enjoyed meeting you down there in Round Rock at the
Yes.
TNT.
That was a nice show.
It was. Quick question in the chat. Can you put a link in the chat Yeah, well, that's pretty easy. NEMAL.com, Hal. Uh, so certainly do appreciate both of you gentlemen coming and speaking with us. Very interesting. Gives us something to think about and maybe make a plan for the next rebuild studio or transmitter site. Harold?
Yeah, just a quick question on single mode fiber. Is it just that it is smaller and so it's bouncing back and forth less, yet you're still getting pulse dispersion? I've also heard of, I think it's graded index, where the optical index varies as you go out radially from the center. Can you describe single mode a little bit more?
Danny, you want me to?
Yeah, go ahead.
Okay. Well, basically, what you're doing when you use a 9-micron core, and that's a typical single mode core, as opposed to a 50-micron or a 62.5-micron, that was the older size of multimode, it is narrow to the point that the beam of light can only go straight. You were getting a tremendous amount of loss and reflection by the bouncing of the wavelength from the top to the bottom of that wider core. So the performance is drastically better at single mode. Single mode is the typical choice for any broadcast application, although a lot of prosumer equipment still uses multimode. Multimode used to be cheaper in the beginning. Now it's much more expensive than single mode.
I thought that the main concern of multimode was pulse dispersion because of the different lengths the light path is as it bounces around.
Well, yeah, you're getting a lot more attenuation and a lot lower performance of back reflection because of the multiple paths.
Okay. I was thinking pulse dispersion, that the beginning of the pulse gets spread out, the end of the pulse gets spread out, whereas in single mode, it's all going down the same length, like a single piece of coax that's, a certain distance, so you don't get the dispersion.
Yeah, I actually do not have that data, but I could certainly look it up and get back to you.
Okay, no problem. Thank you.
Thank you.
Very good. Okay.
My favorite thing about single mode versus multi-mode is distance. I don't want to be concerned with distance. I'm not trying to get 10 gigabit signals from point A to point B. I'm trying to get one 50 gig signal from point A to point B, and I want to go 20 kilometers. I don't want to go 2,000 feet. So I've seen people design racetracks around multi-mode, and they can't get around the track without having to go in and repeat the light. Whereas single mode, we don't have that problem.
Plus, it's more money.
Yeah, and it costs more money. But it is a data center thing. It is an IT thing. But again, it's not how we do it in broadcast.
Very good.
Barry, thank you so much for this opportunity. It was really, really great and very nice of you to invite us.
Well, thank you. We had between the YouTube and the Zoom, we had about 60 people with us today, and a lot of positive comments here on the chat boxes. So pretty much everybody stayed along because it was very interesting.
Thank
We're
you.
glad.
Thank you.
Have a great day, everybody.
Come back again.
Okay, thanks.